talk about wide area networks for a few minutes. It talks about consumer internet connections, what we have, enterprise connections, and WAN infrastructure technologies. This one actually, compared to the others, is a relatively short session. Module A, wired internet connection technologies, wireless internet connection technologies, and then troubleshoot internet connection technologies. And the troubleshoot really, unfortunately, often is just go to the ISP and say, okay, what's going on? So the wired, and for a lot of years, and not knowing anybody's age except my own, it's been slow, and it was slow for a lot of years. If you started, I started trying to get on the internet sometime in the late 80s. Dial-up, very slow modems, analog phone. There were some digital, but at home you had an analog phone in order to dial up. And then a little while, I got a teenager for a son for a teenager, and he was always on the phone on the internet to do those things. So you wind up with two lines here, but 56K is where we're talking about. Maybe up to 128K. We're not talking about megs here, we're talking about K. Not a whole lot of images got transferred with those things. Most analog, some had digital, ISDN, and then ISDN was one that was advertised as a business phone that was actually probably the start of the T1 lines, but they were expensive, and you had to have some place to connect it to. You had to have a provider that would take those connections to do those things. Business lease lines, the T1s that we talk about, there were a lot of dial-up from businesses also to do those things, but the lease lines were always on, and the always on are, way down here at the bottom we say symmetrical and asymmetrical. Symmetric is an always on, and asymmetric is an on demand. A dial-up would be an on-demand system to do those. None of these things, none of this was even close. When we got cable modem, and the cable modem at that time was 10 meg, it was night and day. It was just absolutely phenomenal. And now we're talking 200 meg, and we talked about the wireless a little earlier, probably 4.5 to 7 gig bits per second. So, we've come a long way in a not very long time in the perspective of things and in the normal development cycle. So the table down at the bottom, technology, dial-up, less than 56K, analog phones, ISDN 64 to 128K, used a digital phone, DSL, which is one of the ones that we use today, 256K to 100 meg. Not as fast as we're going to get with cable, because broadband cable 384K to 400 meg. And I don't know what you guys get for your cable modem. If you have cable modem, they are advertising, and I can see 200 meg here, but it depends upon the equipment that you have. I have a neighbor down the street who has never upgraded his equipment since they put it in. I was helping him the other day, and we did a speed check, and first I got 1 meg. Then we moved some things around, checked the cables, be sure that they were seated properly, and got all the way up to 10 meg. But he's paying for a 200 meg line to get there. Fiber, the one at the bottom there, up to a gigabit. And we're going faster and faster and faster with these things. It's kind of a real time. And then all of this faster speeds, again, allows us to do what we're doing here tonight, which is to be in a meeting together and go over this material, present this material that hopefully is making some sense. Hopefully the mud's getting a little bit thinner as we go through. I know that it was like really thick mud after Monday night. The question then becomes, who owns what? Until I think it was probably the late 80s, early 90s, maybe late 90s sometimes, the phone company owned everything. It didn't matter what it was, they owned it. If you wanted to put a phone in, move a phone around, the phone company had to do it. and then we deregulated. I guess that would have been in the 70s. I think it was during the Carter administration. We deregulated the phone companies. And when we deregulated the phone companies, we now own the wiring inside of our house. We can own our phones. We do own our phones. We can make modifications to what's going on. But in order to know who owns what, we have to have this thing called a demarc, a demarcation point. And it's the point where the ownership transfers from the phone company to you and me, so that if something happens to the wiring inside the house, I'm responsible for it. Something happens to the wiring on the other side of the demarc, the phone company or the cable company is going to be responsible for it. So who owns what? The demarc, and the demarc is a point of entry into a building. Use a demarc with the ISPs today, and the ISP here. We're not going to be talking about the ISP for you and me for the cable modem for the spectrums of the world, but for our business. And the could be something they're talking about as simple as a physical connector, and the physical connector is a T1 smart jack. A T1 smart jack is going to be a CSU DSU. The smart jack actually moves the demarc to that point. The network interface device, termination device, or the optical terminal are going to be the things that will be the demarc themselves. A formal boundary between the premises wiring, us, and the local loop, sometimes called the last mile coming in or first mile going out. It depends on your perspective as to which it is, but the local loop is the last bit of wiring that comes into our system. And the connection, what the connection is, depends upon the technology that we're using for these things. Some of the ones that we have dial up, and I don't know, I guess that people are still, if you can't get anything else, dial up is what you would do. So to me, and I may be all wet, but to me the order of preference to get these things would be cable modem, although people hate the cable companies, but cable modem is generally going to be quicker, and then maybe a DSL, a wired connection. After that, probably we're going to talk about WiMAX, a wide area network wireless, and then satellite, although it's pretty bad in itself. And then after that, the PSTN, publicly switched telephone network, and POTS there is plain old telephone system is what those things stand for. The dial-up, analog phone, analog systems, slow speeds going to the ISP and the internet. The one in the middle there is the ISDN, the BRI, the basic rate interface, and it's broken up into 3 different areas there. 2 bearer channels, and those are going to be B channels. And then they're each 64K, so that's where we get the 128K for the ISDN. The 2 64K B channels are bearer channels, and then a 1 16K signaling control channel or signaling channel, and it's going to be 16K. So we have 2 Bs and a D to operate on these. The terminal adapter is the device, and since it's a digital system already, we don't need a modem, but we have to have something to prepare the signal, and that's what they usually say. The CSU, DSU, and the T1s prepares the signal. The terminal adapter prepares the signal for transmission on the internet when we do those things. So the B channels, voice or data, are equal to 1 voice line, and the voice lines are going to be the 64K lines. When we get to T1s, T1 is actually a sequence, a series 1.544 meg, which used to be just absolutely wild, is a combination of a bunch of 64K lines. The DSL, digital subscriber link, down here, data is carried along with the voice. They use different frequencies. If you have DSL, my mother had DSL, it was okay. It was better than dial-up most of the time. But filters there, you're typically going to have filters on your voice phones to filter out the frequency from the data channel. They've got their own distinct tones that they use in order to send information back and forth. So we want to filter those out so that we don't hear them, put filters on the phones. We're multiplexing, obviously. We're using the same analog line, voice channel, to send data, the digital channel, a digital signal back and forth using these things. So we have the data and the voice on the same channel. The DSL, the speed distance, it depends on how close you are. And again, what we are getting, ADSL is asynchronous DSL. Asynchronous means that we have a different upload speed and download speeds, and most of us do that. When we talk about the cable modem being 200 meg, it's 200 meg down, it's like 10 meg up. So your download rate is going to be higher than your upload rate for these things. And you can see the farther we get from the exchange, and this is in kilometers, the lower the data rate that we're going to get. So we have to be within a certain distance of what's called the central office, which is a switch to do these things. And the ADSL 2 Plus or standard ADSL, depending on what technology is available, what kind of a data rate will you be able to get from these things, from the DSL itself. Cable modem, talked about, and you've seen this picture over here on the left before, baseband. Everybody gets the same frequency. Broadband, we have data, voice, and video, all running on the same piece of wire that comes into the house. It could be fiber, it could be coax, and some providers have now gotten fiber to the house. Most of them are still fiber to the neighborhood, and we'll look at some of that in a minute. The one on the right is the DOCSIS. DOCSIS is the data over cable service interface specification. That's the cable modem. Which version you have and the production date, and look at what it does with the bit capability. 40 megabits maximum upstream capacity, 10 and on down the line, until we get to the 3.1 full duplex 2017. It actually has a 10 gigabit capability, up and down. So when I talk about my neighbor down the street and try to get him to go turn in and get the new equipment, one of the things that is holding him back is going to be the equipment that he has. He's got the old DOCSIS standards. So you can't, even with a high-speed modem or high-speed router, the modem is going to affect what goes on in the system itself. Fiber internet, a number of providers have gone to that. Verizon, with Fios, AT&T's claiming fiber to the home. My provider hasn't done that yet, but high speed, no electromagnetic interference for fiber. We've talked about fiber. It's light waves that go through these things. No EMI, no interference. We can go much further. No real noise. We can go longer and longer distances with it before we have to repeat the signal to do these things. And the question is, and how far does it go? Where does it terminate? To the neighborhood, a cabinet for the neighborhood. Then we do copper, either DSL or DOCSIS, and cable modem is going to use DOCSIS. DSL obviously would be with the phone system. To the curb, a smaller area, maybe a block. A shorter last mile for this. The last mile is from the distribution point to our house. So the last mile is going to tend to be a little faster. And then to the premises is going to be the best way to do it. Into the building. You have a fiber cabinet for termination. When we got fiber into the building, we got a fiber cabinet. And it was a pretty big piece of equipment. That then became the demarc, the point of entry. I mean, it didn't actually have to be where it came into the building. It's where their media ends and their responsibility ends. Their media responsibility ends and yours begins. Then we have copper for the distribution. That's exactly what we had. We had fiber coming into the building, and then inside the building we use fiber for the distribution for these things. Wireless internet, a couple of different ways to do that. Cellular data, mobile phones, probably do that. So you go to a website, you look something up, you Google something, you check Bing, check different things. On the internet, we're using cellular data to do that. They've gotten the data costs have gone down substantially over the years when we do that. Terrestrial wireless, ground-based systems, it's going to be the WiMAX. I have a friend who has terrestrial wireless. He lives out really way out in the boondocks. There is no cable there. He has a phone. Yeah, he doesn't even have a phone. He uses one of the internet things, but he can't get cable modem. He doesn't want to use dial-up. He's too far away for DSL. So there is a company, as long as he has a line of sight to the top of one of the mountains, and this is in Roanoke, there are mountains there, to the top, one of the top of the mountains, he can get this terrestrial wireless, the 802.1, the 802.11 WiMAX, to do those things. The other satellite, he did have satellite for a while, and he really didn't like it because you use satellites for communication. They're one-way or two-way. A lot of what the satellite is you use the phone for the query, the phone line for the query, www.someplace.com, and then the download comes over the satellite. So you can get a lot of delay in those things. They are a long way off. Some of the newer ones have two-way satellite in order to do those things. But the wireless internet here, and these are the speeds that we've talked about, that we kind of have talked about, 3G, 4G, and 5G. The 5G is going to be really, really fast, and it's being introduced in I think some cities this year. It's a 2020 project. But we go back to the 3.5 was 42.2 meg, 4G 100 meg. 4G LTE 150 meg, the advanced we're up to a gig, and then the 5G, the one that's coming, that's being introduced right now, and you have to have new devices obviously in order to take advantage of it, is going to be 10,000 megabits or 10 gigabits per second data rate. And this is the one that they have to redo everything. This is going to be the millimeter wave installation. The WiMAX 802.16, frequency 2 to 66 gig. The theoretical download and upload is 1 gig, and I can tell you that my friend is not getting the 1 gig because he's farther away. He sometimes has issues. He has weather issues, storms, thunderstorms, fog. You have to be careful about what kind of plant life are growing around these things, because a tree grows up, or it's okay in the fall, and then they leaf out in the spring, and it blocks the signal for these things. But WAN technology, it's a wireless alternative to DSL. The range on this thing, 30 miles. And then the types of WiMAX, an image down there, a DSL, fixed WiMAX going to the house, mobile WiMAX to cars, and then portable, different ways to get different processes to be able to get these things. And we have the nomadic here that's wandering, but you still have to have a line of sight to the antenna, to the broadcast antenna. If you can't see it, you can't get to it. Satellite, a lot of technologies, maximum speeds, look at this, up to 50 megabits per second. Got to have a dish, latency due to the distance from the earth, the uplink and the downlink. It is going to be costly. The uplink may or may not be satellite. It may be via your telephone for the uplink, for the www, the query, and then the downlink would come via the satellite. Internet connectivity, the things that we can do or not do, and again, mostly It's just troubleshooting, call the ISP. Speed test, you probably have done that, speedtest.net, a number of places that will do a speed test for you. There are 2 of them in the book, and I put this one in here, and they have just what ping.eu maybe shows you, or does for you. There it is. It has a number of tools on it: ping, trace route, DNS lookup, whois, port check, test if a TCP port is open on a specified IP. We can check to see if ports are open. Reverse lookup, country by IP, by host name. So a number of tools that are available for you at that link if you want to use them. And I said there are 2 of them in the book, and I didn't put the other one in here. I think that I actually put it on. It does a thing. I think I linked it, and I'll get this other browser start here. Or not. I use too many browsers and I lose track of what I did with which. But there are sites that have these things, a TCP/IP test site to do those things. I'll just see if it's on this other one, and it is not. But the tools can be kind of handy with these things. Public DNS servers, the Google DNS server 8.8.8.8. If you haven't investigated it, and this is just me, take a look at OpenDNS. OpenDNS.com, I think it's either OpenDNS.com or .org, is a open source DNS server, and you can configure it to do some screening out for you. I'll try to show you it. Yeah, it is a Cisco organization, and you have to make an account, obviously. And I think this is the one. When you do it in the settings, you can, over here, you can specify filtering, and you can do a custom filtering, things like, you know, drug, sexuality, park domains, hate discrimination, things that I don't want to be resolved by DNS, tasteless, web spam, pornography, German youth protection, and it tells you what these things do, AdAware. So you can, by using this, get an account using this as your DNS server, you can kind of customize things that you don't want to go to. AdAware being one of the big things that I don't want to go to, and different malware sites that they put in there, that they detect. That's what I was looking for, to do those things. It is an open source project, so lots of people are working on it. That's one of the advantages of open source. Instead of just a small group of individuals working on it, a whole bunch of people are working on it. And the last one there, Looking Glass Sites, a public server that has a BGP routing information, and they've got some links to some of those if you want to take a look at them. And how many routes do we have on these things? ISP troubleshooting, and this is what options do I have. And you've probably called your ISP, called your provider, and it's always they're trying to prove that it's your fault. It's going to be your problem. I did that one time, and they explained to me how DHCP works. And it's like, I know how DHCP works. So why can't I get an address? You go around and around with them until finally they help you come to the conclusion, or to the conclusion of what's wrong on yours, or finally decide that it's their problem. And they're going to know if they have a problem, most likely because they're going to have hundreds of calls in. we had they actually had a physical fiber break in Charlotte and lost the internet. Called up, said, oh, nobody's reported it. Well, everybody else was at work. They didn't report it until a little bit later in the day. I went over to talk to my neighbor who had worked for Spectrum and called them, and since they decided that she knew what she was talking about, they came out and troubleshot it and found a physically broken fiber that only affected our block. So you may have to work at convincing them that you have a problem. They're going to assume that we're the problem. It could be interface errors, configuration errors. DNS errors are one of the big ones. Route errors, and this is where our trace route is going to come in handy. Interference, and interference is probably, we're going to be talking about wireless here, and it could be a policy-based issue that goes on that we have an issue with. And then they help us out. They do some filtering also for malware when we do these things. So we have some more assessment questions. Which of the following statements are true? Choose all that apply. By definition, you are responsible for all devices on your side of the DMARC. By definition, your ISP is responsible for all devices outside the DMARC. Sometimes devices on your side of the DMARC might still be your ISP's responsibility. The local loop refers to the customer side of the DMARC. The local loop refers to the ISP side of the DMARC. B, C, and E for that one. What internet connection technology uses the same wires as your analog phone line but a separate communications channel? You see DSL, this digital subscriber link for that one. How many channels are there in a BRI ISDN connection, the B channels? You got A2 for that one. Order these things, and I actually didn't see okay, we'll just do that. Edge, 3G, HSPA, 4G, LTE, and I sometimes look for these things. I do a search of the book, and it's like, okay, where did you come up with this question? Because you didn't mention these things, and I haven't done. I should have done this one a little earlier. I didn't. I did one that was, I don't know, Tuesday or something. That the only place I could see any mention of what they were asking was in that question, not in the text anywhere. So these things may or may not be in the book, but they may or may not be significant in the examination area. I think that we probably can finish this one up and then have an hour's worth of lab time, but we're going to talk about circuit switching, packet switching. Circuit switching, obviously circuits. Packet switching is we can have packets going in a different direction. The issue with that is now we're going to have to depend on TCP to put them back together if they get there out of order. Circuit switch leased lines, and then packet switch wide area networks. Packet switching, each packet may take a different path in this thing, and one of the terms that you may or may not, I haven't heard it in a while, but I have heard it, is on-the-fly intelligent switching, where the packets based upon the information that the routers have, because routers are talking to each other, it's going to take the best path that's available at the time. So they may take different paths to get from one location to the other. And we know that since TCP numbers all of these packets, when they get there out of order, TCP can put them back together in order so that we have the data that we really need. Circuit switching is when you create a circuit in order to make a connection. And telephones did that. A telephone exchange, and the red shows what the switching would be to create the circuit for these things. We have the caller here, going to phone exchange to the call destination. They actually did have switches that failed over and until we got the two lines connected. They do emulate dedicated lines. Inflexible and wasteful because when we have a connection, then the both ends are busy. We can't then do anything else that's going on. And the one here is if you download a page, you're going to sit there and read it. We've got the line tied up while we're reading the page. No data is being transferred, but the line is going to be in use. If we're streaming something on a full duplex, then we've got half of it that's really not being used, because streaming typically is going to use UDP, which is not going to have any messaging back for authentication, for acknowledgments, not authentication, for acknowledgments for these things. Virtual circuits, packet switched is going to be more efficient. The latency and throughput is going to be unpredictable for these things, but we're going to have permanent virtual circuits and switch virtual circuits. And down there, the last two switch virtual are obviously going to be temporary. Permanent virtual are in fact permanent. They're going to be used for an old protocol called frame relay, which is kind of going away. And then ATM is asynchronous transfer mode. The virtual emulated the circuit switch, and the TCP creates the connection. We may have quality of service in the enterprise. Quality of service assigns a higher priority to certain traffic that gets there first. And the other thing that we're going to have here is the SLA, the service level agreement, which is a legal contract between usually the company, not us and the provider, but the service level agreement that we have for that. I'm sure that LeaderQuest has with their provider. They have certain contractual requirements, which can include the data rate, the uptime, all sorts of things are in the contract to guarantee that we have the service that we need. But the virtual circuits, the bottom line of those are we can have permanent circuits and we can have switch circuits. The frame relay, the advantage to the frame relay PVC, the permanent virtual circuit, was that you paid for a minimum data rate, what you thought would be, your absolute bottom line. If there was excess resource available at any time, you could use it. So you normally would be able to go above what you were paying for, because the odds are everybody's not going to be using their minimum at the same time. ATM, asynchronous transfer mode, is kind of the follow-on to frame relay. But in today's world, we're using all of these Ethernet standards because Ethernet's been around for a long time. The T carriers and the E carriers are the dedicated lines. And the T1, 24 user channels, or 24 64K channels with this thing. 1.544 meg. The E1 is the European standard. It has 30 channels. And it's going to be 2.048 T2. Not really used. They usually go from a T1 to a T3. And if you want something less than that, you buy a fraction called a fractional T3. You may want a certain bandwidth. Then, since they're in 64K bundles, you can buy part of a T3 line or an E3 line, and then the T4 is just there so that you can see what the speeds are. That we do have an increasing speed for these things. When you look at the speeds that are available on these dedicated lines, and then what we can get with some of the fiber with the Ethernet variants, they become a lot more attractive than the dedicated and the leased lines. Leased lines tend to be fairly expensive when you do those. The CSU, DSU, and I think they say they use a different term, and I changed it in the slide in the book. Carrier service unit, I think they call it. channel service unit, I checked with Google, and they said that channel service unit is the term that should be used there. CSU, DSU. CSU, DSU on a router is just a module that plugs in, that you plug in your line that goes to the ISP to it. The T&E they were originally, the T lines were originally designed to digitize voice, but they became popular for lease line channel bonding the 64Ks, the T1s, bonding the 64K channels together to give us a high-speed internet connection. High speed at the time, 1.544 meg, not so high now. Advantage to a lease line is it is going to be symmetric. You're going to have the same up and the same down. So your web server that is going to be able to respond, people coming into it, then you're going to go out with the same speed. CSU, DSU prepares the signal for transmission on the internet. It does the same purpose as the modem does. And again, the lease lines are going to be fairly expensive when you do that, particularly with all the other alternatives that are available, like VPNs through the internet. Optical carriers, and we've talked a little bit about optical, fiber optic. After the digital, the next big change was optical. It's going to be faster. It's going to go farther before we have to repeat it because we don't have noise. The rest of the world, so the U.S. North America uses the SON, the Synchronous Optical Network Standard, and the rest of the world uses the SDH, the Synchronous Digital Hierarchy Standard. Multiple channels that go in this thing, 8,000 frames per second when they're in use. They can be a star or a ring. And the ring, a counter-rotating ring, is we have two of them. In case one of the rings goes down, we still have the second ring in order to be able to send information. Counter-rotating ring, we would have a ring here with our devices connected to it, and another one in here just in case. And all the devices we would have our, I don't know why it does that. Our devices in here would be connected to both of these. One of them would be the primary. If it went down, then we would do the other one. Counter-rotating, one of them goes in each direction when we do those things. Originally, optical was used for optical-based multiplexing for these things, and then we have we looked at the carrier wave division multiplexing and dense wave division multiplexing, basically breaking into colors, breaking it into frequencies, and the speeds that we get when we go to these things. We go down here, the OC 768. It's pretty fast. It's about 40 gigabits per second. A lot of the OC standards are used for voice transmission for the long lines that phone calls that voice goes on, or that now that data goes on to get from point A to point B. Point-to-point protocol, PPP, is going to be a standard, that's layer 2 standard that's used for wide area networks. Used for leased lines, it's an old protocol. I talked about how slow dial-up was, and it was, but dial-up actually used point-to-point protocol for its layer 2 protocol. It still does. Point-to-point leased lines use the PPP protocol. If we're in an all, for instance, we're in an all Cisco environment, we're going from a Cisco devices to all Cisco devices, we can use the Cisco proprietary HDLC for layer 2. If we don't have an all Cisco environment and they're not all configured by default for that protocol, then we need to go to a standard, which is point-to-point protocol. And keep in mind that point-to-point, both points have to be configured with the same layer 2 protocol. After we have it, multiple layer 3 protocols, and down here they talk about IPX. IPX is an old NetWare standard that probably went away in the early 80s, but it still keeps showing up in the books. But what the PPP uses is over here on the right, IP Below that, NCP Network Control Protocol. It establishes the connection and checks to be sure that the connection is still up. It actually uses ping in order to do that, to be sure that the other end is still there. And then the IP Control Protocol is, think of it as getting an IP address, think of it as a DHCP, and then the PPP encapsulation. Point-to-point PPPoE, point-to-point protocol over Ethernet, and PPOA, point-to-point protocol over ATM. So point-to-point protocol, layer 2 protocol. It is a standard, can be used on lots of different ones. It supports, it says link aggregation. We talked about Ether channel LACP, link aggregation control protocol, at layer 2. This does the same thing at layer 3, or not layer 3. It does the same thing at layer 2 for a wide area network as link aggregation control protocol did for Ethernet. It allows us to bundle serial ports T and E, and it only works for the T's and the E's, into a virtual interface to give a higher speed connection in the point-to-point protocol. So we can bundle them just like we could bundle the Ethernet with the Ether channels. Packet switched, circuit switched, good for voice and the least lines. A packet switched or PVC is going to be cheaper. They only consume the resources while they are in use. Packet switched, cheaper. We don't have to reserve the full bandwidth. And this goes back to frame relay. We reserve the minimum that we think that we're going to need, and then if there's any excess available, we can use it with it. Reserve a minimum. If you have access, we can use that. Packet switch technologies, frame relay, again an older one, ATM, and then multi-protocol label system, MPLS, which I think the last slide I've got an image of what it looks like, what the shim's going to look like with it, and then carrier Ethernet. Ethernet is becoming more and more prevalent even in longer range applications because of fiber and the ability to send it longer distances, much farther than the 100 meters that we've talked about in the local area network. Frame relay and the extension of ISDN starts at 64K, goes to T1 and T3. It has error correction but no detection. Dynamic, it allocates bandwidth, and it uses a switch virtual connection, a permanent virtual connection. DELC there, data link connection identifier. That's the configuration that we have to put on the devices so that the system knows where to send it from to. And what this is a switching network, frame relay is. So we have the WAN cloud in here. This is going to be the frame network. It's going to have frame switches in it. We have a frame relay switch. We connect to it. It goes into the cloud. Based on the DELC, the data link connection identifier, it'll put us on a path through the cloud to go to our destination location. Any configurations that we would have to do are moderately uncomplicated at our end, but in the ISP in the cloud itself, a little bit different situation. They have to actually program the switches to go from one to the other. And this one over here is an attempt to show what the cloud might look at. We talk about DTEs and DCEs. DTE, data terminal equipment, that's what we would have. Data communications equipment would be at the ISP end. There is not a lot of difference in their routers generally. All this here switches because it's a frame switches in a frame relay cloud. But the difference between a DCE and a DTE is the DCE has a clock rate on it, and it sends the clock to the DTE so that all of the communications will be synchronized with them. ATM, asynchronous transfer mode, is designed, it says, to overcome frame relay shortings. It is a fixed size cell. They're going to have 53 byte cells, very high speed over the PSTN DSL. Down here, the virtual path, we're going to have a path definition on the physical length, and then we're going to have the different elements that are going to come into the virtual path to send the data. Again, getting data from point A to point B is all what all of these things are about, is going from one to the other. The ATM cells replace the Ethernet frame fixed link cell with a 48 byte payload. Back here, we say the 53 byte cells, that includes the header information, the overhead information that goes with it. It doesn't limit the MTU, the maximum transmission unit, 48 bytes. Remember, it was what, 1500 bytes for Ethernet. What it does is it segments, it breaks them apart, and then it does a reassembly, the segmentation and reassembly. And the key for these abbreviations, I had 269, and when I looked at it today, it looked like it was on page 259 or 260, somewhere in that area. But what each of these things represent, each of these elements of it represent. Metro Ethernet, ATM looked to be dominant, and this is where we get with the Ethernet, the 10 gigabit Ethernet, well established. It's going to be cheaper, and we're going to go from Ethernet to Ethernet. It's going to be easier than going from one standard to another standard. The optical standard, we can go tens of kilometers with the optical now. So the infrastructure is going to be cheaper when you look at the ATM infrastructure and all of the translation that has to go from one to the other, and then to use the gigabit, the longer distance gigabits. And the Metro Ethernet is typically going to be use a point-to-point protocol over Ethernet to do these things. Cheaper infrastructure, same data format, Ethernet data format, reduced overhead. We don't have ATM headers, and we don't have ATM. Uses carrier Ethernet, and then the local loop, last mile, is going to be Ethernet. And over here, the advantages of it: flexible, reliable, cost effective, easy to use. We can use quality of service, and it's going to be scalable when those protocols are used. The MPLS, the label switching, what this does is avoid using the IP address. What it puts a shim in, and the shim is up here. We have a label value, and the label value is going to have a path across an MPLS network. And it has to be an MPLS enabled network. The ISPs are going to use this. They use this process to make the data transfer faster. It says it's carried in layer 2, or it's sometimes called layer 2.5. It actually, the shim gets put between layer 2 and layer 3, between the MAC address and the IP address. The hardware that's required, we have the customer's edge, that's us, our router, and then the provider edge. Here is a label edge router. So as we go into our provider, whoever it may be, it's going to start putting labels on these things. And it's going to insert this shim, and the shim is then going to, based on where it's going, and it just shows straight line routers, but you would have a whole lot of devices within the ISP cloud. It selects a path to go from one location to the other. So we go into it from the label edge router, puts the label on it. The LSRs are the label switching routers, and the LSP is the labeled switch path. So the path is predetermined based on the labels. And when it gets to the end, it's called a pop, and it pops it out. It takes the label off and then sends it to the customer edge over here to the customer device without any of the labels on it. Because if we did any of these labels with MPLS or with frame tagging with 802.1q, we sent that to any of our standard devices that need standard protocols, standard packets, it's going to reject it. So these things is only used within the cloud of the individual providers that use the MPLS structure. So we are, and we did get this one, I think. So we have some more review questions. Which of the following statements are true? Choose all that apply. Circuit switched networks are better for emulating dedicated point-to-point connections than packet switched networks. Packet switched networks are better for emulating dedicated point-to-point. Early Ethernet standards were circuit switched. Historical telephone networks were circuit switched. The right protocols can help packet switched networks emulate a circuit switched network. A, D, and E. So we'll go with that. Which of the following is true of carrier lines? Choose the best response. T and E use identical protocols and data rates. E carriers offer greater data rates on similar hardware than T carriers. T carriers offer greater data rates. T carriers are copper-based. E carriers are optical. Got a B here, and they are. It was 2.048, I think, for the E carrier and 1.544 for the T carrier. What technology was designed for use over ISDN links? Choose the best reply. B. Frame relay. Frame relay is a protocol that is still around, I think, I guess. But it's going away with the other things, particularly all of the Ethernet variants that we can use for these things. And VPNs. Which of the following are true about ATM cells? All that apply. They are always the same size. They are generally smaller than Ethernet frames. They are generally larger than Ethernet frames. They limit the MTU. They are identical regardless of physical medium. A, B, and E. So we got A, B, and E with these. Because of PPP's authentication and data compression features, you'd like to use it to carry TCP/IP traffic over an Ethernet network. Can you do this? Yes, that's exactly what it's for. Yes, but I need something else. No, and no. Yes, and you do, and it's called PPPoE, point-to-point protocol over Ethernet. What we actually do is encapsulate one protocol within the other protocol for certain distances. So we talked about the consumer level internet, broadband technologies, the terrestrial and the satellite wireless options that were available to some people. And obviously, in order to use any of these things, it's got to be available to you. Circuit switched and packet switched networks. Circuit switch creates a circuit. Packet switch is a temporary thing. Doesn't really tie up the systems when we do those things. And both are used by enterprise customers. And again, that takes care of this one. And that as far as